the conference. Thank you for coming to learn in the weekend. So our first speaker is Professor Kulis from Boston University. The title is New Directions in Numerical Learning. Welcome, Brian.
All right, thanks very much. Thanks for the invitation, and thanks for coming out on a holiday weekend. So I'm going to talk today about the problem of metric learning, which is a type of supervised machine learning problem. So I am at GU, and I also work at Amazon in the Alexa group, where I work on machine learning for Alexa. This is work that's been done with a number of collaborators, some of the recent ones. So when we think about typical supervised machine learning, you usually think about classification and regression. The setup, as we all know, for classification is you have a bunch of data points. I give you a bunch of labels for those data points. I try to learn a classifier, a decision surface to separate those two classes to apply that on new data. Okay? Same kind of thing for regression, except you don't have labels, you have real data. Now sometimes the form of supervision may not be simply class labels or regression labels. So for example, if we have a similarity search problem, so we have a database of images, and we want to be able to do retrieval on those images. So I get a query, and I want to be able to find the most similar image to that query in the database, right? So in order to do that, what I need is some sort of distance function, some sort of metric, to be able to compute the distance between the query to every point in the database, sort them, rank them, whatever, and then return, say, the most relevant images. Okay? So there are a couple of issues here. One is we need a distance function, and two is if we are to learn to use supervision, supervision doesn't usually come in the form of class labels in this case, unlike in classification and regression. The kind of supervision that that you would get might be something like similarity information or relative constraints. So so what does that mean? So for example, if I'm Google and I have a query and somebody clicks on link 3 instead of link 2, that gives me some information, some supervision that query 3 is more similar to, or sorry, link 3 is more similar to the query than link 2. And that's a form of supervision, but it's not a form of like a class label like you would see in standard classification. Another kind of supervision that you might get instead of a class label is similarity information. So I might say, I know that these two objects are very similar. Or I might know that these two objects are very dissimilar. Okay. So when you do metric learning, what really characterizes metric learning as a form of supervised machine learning as opposed to standard classification or regression is two things. One is the type of supervision you get in a metric learning problem is different. It's not class or regression labels. And secondly, the loss functions are different than what you get in classification. So instead of looking at squared loss or cross entropy or something, you look at loss functions that depend on this supervision that you get, like your relative distances or your similarity constraints. Okay. Similarly, the applications that people care about in metric learning are typically different than in supervised learning. So supervised learning, you just care about learning a classifier or to predict well on new data. In metric learning, typically you're interested in applications where you want to use this distance function that you've learned from the supervision for things like retrieval problems or ranking problems or clustering, anything where there's distances involved. Okay, so that kind of is the setup. So we can think of metric learning sort of more broadly as we want to learn a task-specific distance function. We're given data, we're given supervision, and that supervision is in the form of usually similarity constraints of some kind or relative distance constraints. And there's various ways to do that. So there's various methods for doing metric learning. So the most common thing to do is just to do what's called global distance learning. Global distance learning says we're just going to learn a single distance function that's going to be applied across all of the data that we have in our data set. Okay? So there's lots of different methods for doing that. You can use a neural net to map the data into some new space. You can learn something other than a Euclidean distance, like a Bregman divergence. You can do linear transformations. And there's all sorts of other things you can do, and there's all sorts of characterizations of a lot of these methods. There's another class of metric learning, which I'm not going to talk about today, which is local distance learning. And that's a different problem. That's where you're typically learning multiple metrics, say one per class, for example, or one per cluster. And that has its own set of applications and its own set of problems and all sorts of stuff. But I'm not going to talk about that. Okay, so we're going to focus mainly on learning a single metric or a single distance function given supervision, and we're going to talk about different methods for doing that. Okay, so here's kind of the roadmap for how we're going to proceed. So I'll start up in the top left corner. There's a sort of the most basic form of metric learning is linear metric learning. It's also called Mahalanobis metric learning for reasons that I don't entirely understand. But it's basically just taking data, learning a linear transformation of the input space, and then measuring the Euclidean distance of points in that map space. That's all that linear metric learning is. It's very simple. You can prove things about it. You can prove generalization error. You can prove regret bounds in the online setting. You can, get global convergence and all sorts of things. So it's very nice from a sort of theoretical perspective. You can prove things about it. Okay. Now we can go in two different directions if we want to move beyond the basic model for metric learning. One thing we might do is we might want to, instead of just saying, well, I want to learn a linear transformation and then use the Euclidean distance on top of that, we may want to learn other forms of distance or divergence. And so there is a class of problems called Bregman Divergence learning. We learn other classes of distance functions other than Euclidean distance. So I'll talk a bit about that. That also has the nice property that you can prove things about it. Then the other direction that we can go in instead of, from linear in another way is to go nonlinear, learn nonlinear transformations, and that leads to what's known as deep metric learning. And once you get into deep metric learning, things work great, but you can't prove anything about anything. So the theory goes out the window, but then the models themselves are very powerful, and you can use them on all sorts of interesting problems. And then there's also a new thing, which if I have a little bit of time, I might mention, which is kind of doing both of these things, which I call deep divergence. So that's where we're going. This. Okay, so let's just first think about the linear case. This is the easy case. So let's say I have a bunch of data points. I want to do similarity search. So I have red points, I have yellow points, and I have a query, which is this white point. Now, if I were to take this query, this white point, and measure the, say, nearest neighbor, say I'm doing like a similarity search and I'm just going to return the nearest neighbor. The nearest neighbor here is this guy right here, this yellow point. And so if I'm just doing a standard similarity search with the Euclidean distance, I would just return this as the nearest neighbor. But if you look at this, that doesn't seem to sort of respect kind of what you would expect or the geometry of what's going on here. You would expect that this is probably actually, this is most likely a red point. Okay? So what you might want to do is you might want to apply some sort of linear transformation to this data, right? Shrink this down, and then now measure Euclidean distance in this map space, just linearly transformed to look like this. And now if you measure the nearest neighbor here, it's going to be this red point. So you're going to map to a space where the nearest neighbor now captures the expectation of what you think the label should be. And so we're going to learn that. We're going to learn that using supervision, using distance constraints. Okay? So in the linear case, as I kind of alluded to earlier, we can think of this as a transformation learning problem. So we're going to just think now about linear transformation, so stretching and rotating of the data. So we have a bunch of data points. Whoops. We have a bunch of data points, which are, say, x1 through xn. And we want to learn a transformation, which is just going to map this linearly. So G here is this linear transformation. G times xi is now the linear transformation of the linearly transformed data. Okay? And we're going to be given supervision. So we're going to encode that supervision as a bunch of loss functions. Whoops. As a bunch of loss functions. There's going to be capital C of them. And so each loss function is now going to encode something about the supervision that we had. 2 points, say xi and xj should be similar. 2 points xi and xj should be dissimilar, something like that. In general, we can write the supervision as a function of this matrix. This is just the inner product matrix of the mapped data point. So G times X is the map data, this is the GX transpose, and now this is the dot product. So we're going to assume that your supervision is a function of this matrix. You can write distances or inner products in terms of this matrix. So the optimization problem that we want to solve says, okay, we're going to have a bunch of supervision, C different loss functions. Each one of those loss functions is going to depend on this inner matrix or be a function of this inner matrix. And we're going to find the matrix G, the linear transform G, to minimize the sum of those loss functions. Okay. So that's really all there is to it. And what you can do is you can introduce a change of variables. You can replace G transpose G with A. Now A is a positive semi-definite matrix. Okay, so now this becomes kind of like a semi-definite program. And so now you've just done a change of variables. And then you typically do one other thing, which is you introduce a regularizer. That's to avoid overfitting. So that's a regularizer on the transformation matrix A and some trade-off term lambda. So here what you get is kind of the generic metric learning empirical risk minimization problem, or regularized empirical risk minimization problem. You have a bunch of supervision, it's encoded here. You have a regularizer to smooth things out, to avoid overfitting. There's a linear combination of those two things, and you search over the space of now positive semi-definite matrices. And so, if you're familiar with regularized empirical risk minimization and classification as a very similar form, there's a little bit more structure because we're looking at matrices instead of weight vectors. Okay, so that's the generic loss function for linear metric learning or Mahalanobis metric learning. And there's probably this is like just a short list. There's at least 1,000 papers that basically look at different versions of this model. Right? This goes back to like 2002 or something. So this is pretty old in machine learning terms. So there's lots and lots of papers that basically all they do is they take that model and they say, well, here's how we're going to specify the supervision, here's how we're going to write the regularizer, and here's how we're going to perform the optimization. and it's just a matter of sort of picking and choosing. Some of these sort of try to prove things about different versions of this model, but you know, at the end of the day, it's all just sort of special cases of that. So a couple examples, which we don't really have to talk about in any detail. There's something called LMNN that's quite a popular linear metric learning approach. And in LMNN, your supervision is in the form of relative distance constraints. So you say you have triples, xi, xj, and xk, and you say that xi is closer to xj than xk, and so you know, typically you would bring this up into the you use a Lagrange multiplier and you make it unconstrained, and then it turns into the special case of the previous model. And then you have some sort of, this is kind of like a regularizer. Similarly, and there's another method called ITML, Information Theoretic Metric Learning. Here your regularizer is something called the log determinant divergence. And you have similarity and dissimilarity supervision. So points xi and j that are similar should have a small distance, and dissimilar should have a large distance. Okay? So again, you know, these are two different models of many, but they are examples of how you might instantiate this empirical risk minimization framework in two specific ways. Okay. Let's see, how are we doing? Good. So, you know, I don't want to talk too much about linear metric learning, because this stuff is like 10 years old, and very, very much in the sort of world of machine learning, you know, classical. So I don't want to kind of go through this too much, but I'll just say a couple more words about linear metric learning. I'll go through one little result that we showed several years ago, and then we'll move on to sort of more recent stuff. Okay, so some of the problems with metric learning, linear metric learning, is one is that this transformation that you're learning, it's a matrix. So you're learning this matrix A. The size of A is d by d, where d is the dimensionality of your data. So this thing grows quadratically in the dimensionality. So that's kind of a problem if you're talking about million-dimensional data. So that's one drawback to global metric learning or linear metric learning methods. There are also many cases where a linear transformation is not really sufficient. It's not enough. If you have, you know, complex data like images or text or something, however you initially sort of represent the image, just a linear transformation on top of that is typically not sufficient. Existing algorithms also don't tend to scale very, very well. Okay. So one of the things that we looked at several years ago to overcome some of this is through the use of kernelization. So I'll give you kind of a quick overview of what that idea is. So the main idea is we're going to take that learning problem that I mentioned a couple slides ago, we're going to write it in terms of inner products, and we're going to replace those inner products with kernel functions, and that's going to actually make the problem scale, it turns out, independently of the dimensionality of the data. So it allows you to go to very high dimensional spaces. Okay, so so we want to rewrite this optimization problem to be independent of the dimensionality of the data, and we need just one assumption in order to do that, which is that the regularizer is something called a spectral regularizer, meaning that you can write it as a regularizer over the eigenvalues of the matrix A. It's not restricted because most regularizers that people use break down this way, so something like the squared Frobenius norm or the trace of a matrix, they satisfy this property, so this is not particularly restricted. So it turns out what you can do is you can take the original metric learning problem, here it is, you have your supervision, you have your regularizer, and you can define a new problem. It has the same loss functions, it has the same regularizer, but the arguments to those are different, and now what you have, in fact, is you have to form this inner product matrix or this kernel matrix, X transpose X, and so this becomes inputted here, and now you look for a matrix KA, which is, instead of being a D by D matrix, is now an N by N matrix. So in here, this was over the space of D by D matrices, where D is the dimensionality. This is now writing a problem that's over N by N matrices, where N is the number of data points. So the bottom problem actually scales independently of the dimensionality once you have this matrix capital K. And so what's the relationship? So it turns out, which you can show, these are like kind of dual problems to one another, similarly to what you see like in an SVM. In particular, if you solve one problem, you can get the solution to the other one and vice versa. So there's a set of equations here. If you have the optimal for one, and you want to get the optimal for the other one, you can just construct it, and vice versa. So this says that you can actually rewrite the problem in such a way that we can make it scale with the number of data points instead of with the dimensionality, and that actually allows us to move to very high dimensional spaces. So that's one flavor of results, kind of results that we looked at several years back to sort of make linear metric learning scale in dimensionality. Okay. So this is basically the same thing, so I'm going to just kind of skip that. Okay, so let's kind of move on now. Let's talk a little bit about what happens when we go beyond sort of the basic linear metric learning model. So if we're going to move beyond linear metric learning, we're going to start thinking about how we can learn other kinds of transformations. So instead of learning a linear transformation from your input space to your output space and measuring the Euclidean distance in that embedded space, we might try to learn some other nonlinear function. And the natural thing to do, especially given all the work in deep learning, is to try to learn some sort of neural network that takes your input, it embeds it into a new space, and then you measure Euclidean distance in that embedded space. So that's really that's all there is to deep metric learning. And this kernel stuff is actually kind of also can be placed in that framework, because if you use nonlinear kernels, but let's not go there. So another approach to move beyond the linear space is to learn something other than Euclidean distance. And so I'm going to talk also about this notion of learning a Bregman divergence, which is a broad class of distance functions that includes squared Euclidean distance, Mahalanobis distance, KL divergence, Bregman divergence, and others. It's a broad class of distance functions that strictly generalizes what linear metric learning is doing, because it includes these linear transformation models as special cases, but it includes other kinds of distance functions as well. So those are the two kind of generalizations that I want to focus on here. So I think what we'll do is we'll start with the Bregman divergence problem, which is, again, it's not deep in any sense, and it is, again, you can prove things about it, and so we're still in the realm of sort of being able to say things theoretically. But when we move to deep learning, then everything's out the window in terms of any sort of theory. Okay, so Bregman divergences. So if you haven't seen Bregman divergences, they are a class of, they're not distance functions because they don't satisfy the triangle inequality, but they're a class of divergences, so they measure some sort of notion of distance between two objects, in this case vectors, and they're parameterized by a strictly convex function phi. So I give you a strictly convex function phi, and then I plug in this definition, and that gives me a divergence. So for example, if I choose phi of x to be the square root 2 norm of a vector, then you just work it out, and the Bregman divergence is just squared Euclidean distance, just between x and y. So it's the 2 norm squared of x minus y. If I use this other strictly convex function, I get the KL divergence as a output of the Bregman divergence. In general, what's going on geometrically is you have a strictly convex function phi. Okay, you have points x and y, and what you're doing is, if you look at the definition, you're taking a Taylor expansion about y, and then you're looking at the difference between the convex function at x and the linear approximation that is based around y, but evaluated at x. So here's your linear approximation. Here's the difference between phi of x and then that linear function evaluated at x. Okay, that's the geometrical interpretation of the Bregman divergence. Okay, so Bregman divergences have some nice properties. It's always non-negative. It's equal to 0 if and only if x and y are equal. It's not a metric, so that's why we don't call it really metric learning or Bregman metrics or something. There's no symmetry here. So d of x and y is not the same as d of y comma x. It also doesn't satisfy the triangle inequality. It is, however, it's strictly convex in the first argument. In general, it's not strictly convex in the second argument. It has this 3-point property here, which is like sort of law of cosines. Okay, so those are some properties of Bregman divergences. So what we would like to do is we would like to generalize the notion of metric learning. Instead of learning a linear transformation followed by Euclidean distance, let's learn a Bregman divergence from data. Okay? So given the same kind of supervision that we had before, which is similarity distance, or similarity constraints, or relative distance constraints, or whatever, we have some task like ranking or similarity search, clustering. We want to learn a task-specific Bregman divergence using that supervision. Now, this learning problem is strictly more general than the previous model, because if you choose x transpose AX for a positive semi-definite A as your strictly convex function, that actually encompasses everything that we talked about earlier in the linear case. Okay, so you can get all sort of Mahalanobis or linear metric learning models as a special case of this, but this is now strictly more general because it includes other things, like other kinds of divergences. Okay. The challenge here is that if you're trying to think about it from a machine learning perspective, how we're going to learn a Bregman divergence, it becomes a little tricky because Bregman divergences are parameterized by a convex function. So the learning problem for metric learning now, or divergence learning, corresponds to learning a convex function, which is not something typically in metric learning that we deal with. Okay? So here's the, we can go and we can set up a loss function that's analogous to what we had in the linear case. We're going to have a regularizer here. Now the regularizer is on our convex function. We're going to have this trade-off term. We're going to have some supervised loss functions, and that's going to be a function of some supervision, which we'll encode as y. This is the data. This is the Bregman divergence corresponding. So you can kind of set up a loss function analogous to what we had in the linear case, but now it's a function of a strictly convex function. Okay. So it yields a minimization problem over the class of strictly convex functions, which is a trickier thing to deal with than just learning, say, a bunch of weights or a matrix. Okay? So here's what we're going to do, and I'll justify this in a second. What we can do is we can actually approximate a strictly convex function by just a piecewise linear, non-strictly convex function. So if I have any kind of strictly convex function, and I just approximate it by a piecewise linear function, in particular of this form, it's just this is called a max affine function. You take a bunch of lines, and you always look at the max, and so you get a convex function out of this. It's always a convex function. Okay. So we're going to approximate strictly convex function by these piecewise linear functions. And now once we're doing this approximation, we can now learn the corresponding weights of these, or corresponding values of these different lines, different hyperplanes. And so now we can turn this from sort of a problem that's unclear how to do optimization, or to a problem where we can actually do optimization. Right? Now, to justify why this is a good idea, you have to, first thing you have to do is you have to show that if you have any strictly convex function, if you approximate it with a piecewise linear function, that's a good approximation with enough lines. Okay, and so I'm not going to go through this in any great detail, but what we can show is you can show basically so you have phi here is just some strictly convex function with some it's Lipschitz and it's strictly convex Lipschitz and it also satisfies this property. So we take any convex function, strictly convex function, and now we're going to construct a piecewise linear function, and that is going to this class is going to be FPL, where L is bound on the one norm of the weight vectors. And what you can show is that you can get arbitrarily close to any convex function with an appropriate piecewise linear function. And so you get something that grows like k to the minus 2 over d, or for the gradients k to the minus 1 over d. So it's k gets large, this goes to 0, so you can approximate this arbitrarily. Similarly, you can go one step further and say for any Bregman divergence, if you have some ground truth Bregman divergence, you can approximate that Bregman divergence using a piecewise linear function, and you can get to within arbitrarily high accuracy in terms of the Bregman divergence values. Okay. So this gives you a justification for why we can use piecewise linear functions, and this is also we're going to use this later when we start proving things like generalization bounds. So I don't have a lot of time, so I won't go through this, but I'll just mention what you can do now that you've parameterized this in terms of piecewise linear functions. You can set up loss functions and optimization problems where you're learning these lines, these hyperplanes, and typically what you end up getting is either a linear program or a quadratic program, depending on the regularizer, depending on the setup of the constraints. And so you can actually get all sorts of algorithms here, and we have a paper on this if you're interested. And the nice thing is then you can actually start proving bounds about this, like you really care about if I learn if I have a bunch of supervision and I learn some sort of convex function, I use it to generate a Bregman divergence, how well is that going to perform on new data, right? That's typically what we care about in sort of learning theory. And so without going through that in any great detail, I'll just mention that we have bounds for both sort of classification and regression scenarios for how well we actually approximate, how well we get generalization bounds in those settings. Okay, and that's a whole separate thing, but we can actually prove those. And interestingly, the bounds that we get actually match the bounds that already are known in the linear case. So we've moved to a much broader class of learning problems where we're going from learning a linear model to this general Bregman divergence model. but the bounds actually match what are known in the linear case. So we don't actually, I mean, there's, I think, a constant that's worse, but in terms of asymptotic performance, it's the same. Okay? So you can, you can do things like, here's an example where you take some, this is just a regression problem, so I have some ground truth Bregman divergence, which is either the KL divergence or the log determinant or a cyto distance. These are three known Bregman divergences. I can just generate synthetic data and then measure pairs of, measure the divergence between pairs of points. And then I can try to sort of do this in a linear setting and learn a linear metric. And that doesn't work very well because the data doesn't follow a linear, it's non-linear, the distance. And so instead you can learn an arbitrary Bregman divergences as you get more training points. The regression error is going to 0 in all three cases. So that means it's doing something reasonable. We also applied this, this is just a lot of numbers, but we applied this to problems like ranking problems, nearest neighbor search, clustering problems, and we compared with a lot of the existing metric learning work, and it tends to outperform linear metric learning, particularly for ranking and clustering. So, for whatever reason, it works very well when you're doing ranking and clustering. It does comparably when you're doing nearest neighbor search, as opposed to linear metric on real data. Okay, so I'm running out of time, so I'm just going to sort of quickly talk a little bit about deep metric learning, and I probably won't get to the divergent learning stuff. Okay. So deep metric learning is, in some sense, is very simple. We're going to take our model, which is what we had before, which was, measure or find a linear transformation for your data, call that G, measure the squared Euclidean distance between the linearly transformed data. We're going to replace that with just some function, f of x and f of y. So now we're going to measure Euclidean distance between f of x and f of y. And in deep metric learning, we'll let f and y, we'll let f be just a neural network, deep neural network. Okay? So instead of learning a linear function, we'll learn a neural net. Otherwise, everything is the same. Okay? So a couple examples of what people look at in deep metric learning. There's something called Siamese networks and something called the contrastive loss. This is very popular. So you take your two inputs, you pass it through the same neural network, and then you measure what's called the contrastive loss. And the contrastive loss just says if, basically, it says if x1 and x2 are similar, the loss should be small, or the distance should be small, and if x1 and x2 are dissimilar, then this distance should be large, and this loss sort of captures that. This loss actually, I believe, was looked at previously in linear metric learning, so it was the same loss that came up in some linear metric learning models where instead of f, you had g of x, g times x. Okay? But that's one loss that people use in deep metric learning. Another one is there's something called the triplet network, which is nothing but sort of a relative distance comparison model where you have now, you apply on 3 inputs, you apply your neural network, they have the same weights, you apply this triplet loss, which again says 2 points should be, have smaller distance than the 2 other points. That's all it is. Okay. So what I looked at, and this was done with one of my students, Shide, we looked at the problem of deep metric learning for ranking. Okay, so oftentimes when we're doing metric learning, we care about retrieval. That's one of the major goals of metric learning. So we want to have good retrieval performance. So what we want is we're going to use our learn metric. We're going to take a query. We're going to sort the distances to all some objects in some database, return a ranked list. And so we're often interested in some sort of ranking loss function, like average precision. Right? So what we became interested in is how do we do metric learning when our loss function is average precision. Average precision, briefly, you have a query, you have your set of returned results, and there's the precision, which is the fraction of the retrieved items that are relevant to that query. There's the recall, which is the fraction of the relevant items that were retrieved. These depend on how many items you've returned. And then the average precision just looks over an increasing number of items that you've returned and looks at the sum of the precision times the change in the recall. That's called average precision. Okay? It's not super important how it works or the intuition behind it. But the point is, so the supervision there tends to be a little bit different from a typical metric learning scenario. In a typical metric learning scenario, I give you pairs, these things should be similar, these things should be dissimilar, or triplets, like these things should be more similar than these things. Okay. In an average precision kind of situation, my supervision would be, for this query, here's the set of sort of ranked items. Here's the most similar ranked items, here's the ranking that I'm looking for. Okay? And based on that ranking, I can measure an average precision loss. Okay? So it turns out this is very difficult because the loss function is not differentiable. You have to sort. You take your distance function, you sort. Okay, sorting is not a differentiable operation, so you can't back propagate it. Okay? So the main thing that we did, which is which I won't talk about in detail because I've only got about 2 minutes, is we actually provide an approximation to average precision that's continuous and differentiable. And that allows you to then back propagate this sort of approximate average precision so that you can apply it as a loss function in the deep metric learning study. Okay? So we did that, and then you can try applying this on sort of retrieval problems with real data. So we looked at a bunch of different images like Stanford online products, just like a bunch of product images. These are just standard benchmarks for computer vision image retrieval. And you can compare it to all the existing, not all, but many of the existing deep metric learning approaches, and our sort of fast, approximate average precision method actually is getting state of the art on all 3 of the benchmarks. We also did a separate kind of thing where we embedded that metric learning component into a larger system for fashion retrieval. And so in this case, what we did is you have a query. So you have I want to find the most similar products to this piece of clothing, and it returns some similar objects. And then you say, well, actually, I want to change the color from black to yellow. So now re-rank. So we have this sort of re-ranking scheme where you can give it, we call it attribute manipulation. You say, I'm going to change X and now re-rank. So here's my query. I like this, but can you make the sleeves longer? Okay, re-rank. And I like this, but can you make it longer or floral, right? And so this fashion retrieval thing actually, it uses metric learning, but it uses also this learning of attributes within the images. Okay? Okay, so I'm just about out of time, so I'm going to skip the last thing, which is basically it's just a way to combine the idea of learning a Bregman divergence with doing deep metric learning. This is some very recent work we haven't published yet with a former student of mine, and so I'm just going to skip that. So there's so the conclusion. There's still, so a few years ago, I stopped working in metric learning because I thought, okay, we're kind of done. There's nothing interesting here. We've kind of done all this work that we need to do, but there's actually a lot of interesting problems still, both at a theoretical and a practical level. Okay, there's, how do we kind of prove things in interesting models that are nonlinear? How do we get practical models for deep metric learning when the loss functions are non-differentiable? And then there's other recent directions that we're looking at. So with my student Natasha, who's here, we've been looking at regret bands for divergence learning. So proving that an online learning algorithm that's just looking at one data point at a time can get provably close to the best possible batch model. And there are issues when you get into these sort of divergent learning problems in that case. So anyway, so I think there's a lot of interesting problems. I think there's a lot still to be done. Okay, thanks very much.
Questions? Right?
Yeah.
So for the Bregman divergence case, so we generally use a family of linear function to approximate the normalized function. So when you show the example, like the empirical results, so like I find there are different performance when you use basically you have different feed function, right? Like the carrot divergence or log determinant
Yes.
or the others. So does that mean your algorithm do you need to know some prior information about the field, or is
No,
it just
so
total
when you train those models, so in that case, I think the experiment you're referring to, we're generating the data synthetically from some ground truth Bregman divergence.
Oh, you know the ground truth, they generate just from
Yeah, so that's just synthetic data. And when we learn it, we're just giving like pairs of points and saying these should have a divergence of whatever. It's a regression problem. So the divergence between these two should be 6 or whatever. And so it doesn't know anything else about the divergence. It just knows the value of the divergence for pairs of points, and then it tries to learn what the underlying divergence is.
Okay, so then how far your approximation to the ground truth? Okay,
So so if you go back, what we have is this is the average squared distance between the true divergence and the predicted divergence. So it's getting down to like 0.005 when you get to however many points, and these are harder problems with log determinants, more complicated divergence, but it seems to be a consistent estimator in the sense that they're going to 0 if you give it enough points. It seems to be learning.
Is page ranking a special case of your ranking?
So ranking is kind of it's a little bit different in that ranking loss functions are not usually based on pairs and triples of points. So usually when you do a ranking problem, your loss function is I want to optimize, the ROC or the average precision or whatever. Okay, so it's not exactly. Some people call it metric learning. Some people don't call it metric learning. It's semantics. But the principle is basically the same, which is you learn some mapping or embedding of your data, and then you measure some ranking loss in that space, and that ranking loss depends on supervision, which is not classic. Yeah.
Can we go back to the first the picture? So you show this blue dots and the red dots. Can we go back to
Blue
that?
dots and the red dots.
So here you just show us this idea, right? So we can choose some kind of linear transformation, so then change this essentially the scale of different directions, so that we can simplify the problem. But I think this idea we can think in an alternative way. Essentially here is we can also think this red dots they stay on some kind of manifold, the yellow dots from the manifold, right? So if we just change the point of view, we try to learn this manifold. Then actually, if we try to calculate the distance of the white part to the two manifold, probably we can also get the same answer. So any connection between these two point of view. So if we here learn this manifold, then maybe we can calculate the derivative. Probably we can get the same linear transformation. So any connection or?
Yeah, so that's a good point. There is work in that area. So there's, I'm trying to, off the top of my head, I can't remember the name of the paper. But yes, people have looked at that perspective on it, and it's a very useful one. And actually, there's some very recent work that I've seen where they are basically trying to learn these manifold functions in some way, and you can think of it as another sort of way to sort of generalize kind of what's going on in the linear case, or a way to think about what's going on in the linear case.
Okay, let's separate it.